Okay, so today we're gonna finish up the rest of chapter 18, and then after that, go over like the remaining stuff that Mascal like went over in his lecture notes because I like didn't go to the previous lectures. So I'll look through his lecture slides and then see like what topics we didn't go over those concepts, and then after that do practice sums on the chapter 17, 18 stuff. Right. So the next thing here is going to be alpha alkylating aldehydes and ketones via enamine. So let's say we have this ketone here, and we react that with, let's say, a secondary amine, like that, in acidic conditions. And then second step, some kind of haloalkane. And then the third step, acid and water, right? Do you guys know what the first set of reagents would do to this carbonyl here if we have a secondary amine in acidic conditions reacting with a carbonyl? So if we have a secondary amine reacting with the carbonyl, we are going to form an enamine. So let me draw out the whole mechanism, where the first step is to activate the carbonyl by protonating it with the strong acid we have, H2SO4 here. Once we activate that carbonyl, the electrophile is now stronger. This carbonyl carbon has a bigger partial positive charge, where the secondary amine can come in and attack that carbonyl carbon, pop the double bond onto the oxygen there. That's going to give us this tetrahedral intermediate right here, where we follow the same proton transfer pattern. We deprotonate the group that we want to keep or stay, and we protonate the group that we want to kick out or leave. We want this group here to stay, so we have to make it into a bad leaving group by deprotonating it and making it neutral using the conjugate base that we formed in the first step. Right. That's going to neutralize the nitrogen, which is good because we made that into a bad leaving group and it cannot leave. We want this alcohol here to leave, but we have to make that into a good leaving group. We have to give it a positive charge by protonating it. Right. So once we protonate this alcohol here, we get this good leaving group with the positive charge here. Right. Now, once we have this good leaving group here, we could drive that good leaving group off by forming an iminium bond, the carbon double bond nitrogen, and then kicking that leaving group off. Another way you could think about it is that imagine the leaving group leaves by itself first, like an SN1 or E1 mechanism, forming a carbocation on that carbon there. When that carbocation is formed there, this lone pair of electrons on that nitrogen can make a double bond there through resonance, right? Or you can think of it as like, when we make that double bond, we have to kick out that leaving group right away. So once we do that, we have this positive charge iminium bond, where we can't neutralize it by deprotonating the nitrogen because there are no hydrogens on this nitrogen here. It's just R groups, R group, a double bond here. To neutralize this nitrogen, we have to do an elimination type of reaction. So look at one of your alpha carbons. Use the conjugate base we formed earlier to deprotonate that alpha hydrogen, form a double bond there, and then pop the double bond onto the nitrogen there of the iminium ion. That would give us this enamine here. Right? This is an enamine because we have an alkene next to an amine, enamine. Right? So that's the product after the first reagent here. Think of this enamine as like an enolate. Which atom would be our nucleophile if this is like an enolate here? Which atom is the one that's going to attack an electrophile? Yeah, the one on the far right, which is this alpha carbon right here, because we know that when we do resonance and we form that iminium ion bond, there's going to be a full negative charge on that carbon right there, which makes that carbon the nucleophile. Let's bring in the electrophilic second step now, where I'm going to star the nucleophile, which is that alpha carbon on the far right, and then dot the electrophile, which is that partial positive carbon with the good leaving group. We're going to reform the carbonyl, not carbonyl, iminium ion bond, and then use that alpha carbon to attack that electrophilic carbon and then kick out that leaving group there, right? That gives us this product here. We star the nucleophile atom, new bond between the nucleophile and electrophile. That electrophile is attached to two other carbons, 1, 2, like that, right? So this is our iminium ion bond now, where if we put like water and acid, that will convert back into the carbonyl, right? So this is going backward from imine to a carbonyl by putting water there. Right? To come from the carbonyl to the iminium bond, we put an amine, right? This carbonyl oxygen here is the oxygen of the water there. Okay. Do you guys want to go over the mechanism of how we transform this to this carbonyl as well? Or I guess like familiar with that mechanism, like going backwards to carbonyl from an imine or imine bond. Okay, so let's look at other ways to alpha alkylate. We could alpha alkylate using the enolate instead of the enamine. So let's say we have this ketone here and some kind of strong base in the first step, like NaH or LDA. And in the second step, we have some kind of haloalkane. Right? This strong base here is going to look for the most acidic hydrogen, which is going to be an alpha hydrogen. There's only one alpha carbon that has an alpha hydrogen, which is the right alpha carbon here. The left alpha carbon already has 4 bonds, 1, 2, 3, 4, no alpha hydrogens. So we're going to have this strong base here, deprotonated that alpha hydrogen, form the enolate nucleophile here. Right? Where we know that the alpha carbon of this enolate is the nucleophile, not the oxygen minus, because the negative charge on the alpha carbon is less stable than the negative charge on the oxygen. And because it is less stable, it's more reactive. So when we bring in the electrophile, we're going to reform that carbonyl, use this nucleophilic alpha carbon to attack that electrophilic carbon, and then kick out the leaving group to get to the final answer here. Right? Where this is the star atom, this is the dot atom, this is the new bond between the star and dot. The dot is attached to one more carbon there. So that's another way to alpha alkylate, deprotonate the alpha hydrogen, form the enolate nucleophile, and then do like an SN2 reaction where your enolate is your nucleophile, your electrophile is a haloalkane to get that alpha-alkylated product. Right. Another way that you could alpha-alkylate is do an aldol dehydration to get an enone, and then do H2PDC to reduce the alkene all the way down to an alkane. So let's say we have this aldehyde here, and we put that under NaOH, water, and heat. And then the second step, H2PDC. Okay. So this strong base, water and heat, will deprotonate the alpha hydrogen to form the enolate ion, which is the nucleophile for aldol. Right? This is going to be self-aldol because they only give us one aldehyde, where once we create that enolate nucleophile, it's going to attack another version of itself. So this alpha carbon here is the nucleophile. This dot carbon here is the electrophile. We're going to reform the carbonyl, use that nucleophilic alpha carbon to attack this carbonyl carbon, and then pop the double bond onto the oxygen there. Right? What that's going to give us is this intermediate here, where this is the new bond between the star and dot. This dot is attached to an O minus now because we pushed the double bond, one of the bonds of the double bond, onto the oxygen. The methyl group is still there, and I'm leaving the hydrogen out as invisible now. Right. The next thing is to protonate the O minus using water to get the aldol condensation product. Right. But because we have heat as well, this will go further. It would dehydrate this alcohol by first forming another enolate ion, deprotonate that alpha hydrogen, and generate the enolate ion again. Which gives us this enolate ion here. Now we're going to reform the carbonyl, shift the double bond onto that double bond there, and then kick out this hydroxide ion here, giving us this enone product. Right. Okay, this is the aldol dehydration product here, which is an alpha beta unsaturated carbonyl or enone. Right. Now the second step, H2PDC, will do a midterm 1 reaction where that H2PDC will reduce the alkene down to an alkane, like that. So that's another way to alpha-alkylate the alpha carbon. Right? Where we see at the alpha carbon, we have a new alkyl group there. Right. So let's look at more reactions of the alpha, beta, unsaturated ketone and aldehydes. Right. Or an enone. So let's draw a simple enone here and then do different reactions. H2PDC, which we just did, and let's say Br2CCl4. These here are midterm 1 reactions, alkene reactions. The H2PDC would fully reduce the alkene down to alkane, like that. The Br2CCl4 will add bromines on each carbon of the alkene, like that. Right. Okay, now let's go over 1.2 edition and 1.4 edition of enones with hard and soft nucleophiles. Okay, so the general structure of alpha, beta, unsaturated carbonyl, or a short way to say that, enone, is this here. Right. Let's draw the resonance structure of this enone. We're going to shift the double bond to make a double bond there and pop the double bond of the carbonyl onto the oxygen to get this resonance structure here. Where the oxygen gains a negative charge because it gained a pair of electrons, and this beta carbon here gains a positive charge because it lost a bond, right? So we see that even though there is a partial positive charge on this carbonyl carbon here, there is a bigger partial positive charge on this beta carbon here. That makes this beta carbon the electrophilic carbon for most reactions, for reactions with soft nucleophiles, right? So let's look at the differences between let's say I'm gonna circle that carbonyl carbon purple and then this beta carbon green. And then I'm gonna say soft nucleophiles are your regular nucleophiles that you're used to with SN2 reactions, like CN minus, N3 minus, Br minus, or like X minus, like any X halogen. It could be, this is the new nucleophile that you guys learned here, an enolate, right? Where the nucleophile is not the oxygen minus, but the nucleophile is the alpha carbon here. Because when we draw the resonance structure, we see that the negative charge on carbon is less stable than the negative charge on oxygen, which is why the alpha carbon is more reactive. So this carbon here is the nucleophile, not the oxygen. Another soft nucleophile is going to be an enamine. So when you see a nitrogen like that, it acts the same way as an enolate, where this nitrogen here with a pair of electrons will go back down to form the imine bond and then use that alpha carbon to attack some kind of electrophile. Right? And here's a new kind of reducing agent that, I mean, organometallic reagent that you're going to learn. It is a weaker version of a Grignard reagent, which is the Gilman reagent. You're going to see that as R2 copper lithium. And only adds the R group of the Gilman reagent once. Right? These soft nucleophiles will attack the beta carbon of the enone. But once you have a hard nucleophile, that is able to attack the carbonyl carbon, the weaker electrophile. So some examples of those are hydride ions, R minus, right? Where the hydride ion can come from lithium aluminum hydride, LiAlH4, or NaBH4, or NaH. If you see any of these reducing agents, think of hydride ion, H minus. That is strong enough to attack the carbonyl carbon here. Right? An example of an R minus nucleophile is going to be Grignard, R MgBr, or organolithium, RLi. These organometallics, Grignard or organolithium, is stronger than Gilman, R2CuLi. Gilman is only going to attack the beta carbon, but Grignard or organolithium is strong enough to attack the carbonyl carbon. Right. So other soft nucleophiles that you might see are hydroxide, OH minus ion, alkoxide, OR minus ion, maybe some H2S or RSH, like sulfur reagents, or R2S, right? The easy thing to remember this is the hard nucleophile. Everything else, think of as a soft nucleophile. The hard nucleophile is either a reducing agent, LiLH4, NABH4, or NaH, and the Grignard reagent or organolithium. Everything else is a soft nucleophile that attacks the beta carbon. Okay. So let's look at this example here. Let's say we have this enone, and we react that with LiAlH4 and acid workup. And the other example, let's say we use this Grignard reagent and acid workup. We know that this LiLH4 is a strong hard nucleophile, which is able to attack this weak carbonyl-carbon electrophile here, right? So for this mechanism, imagine the hydride ion of the lithium, the aluminum hydride, attacks that carbonyl-carbon, pops the bond onto the oxygen to get an O- there, which gets protonated by the acid workup second step to become alcohol, right? And the hydride ion that attacked is this hydrogen right here, right? Let me highlight that. This hydride ion is this hydrogen there that attacked that carbonyl-carbon. So we get alcohol here once we reduce that carbonyl. Okay. For Grignard, Grignard is another strong nucleophile that is strong enough to attack this weak carbonyl-carbon. So let's say that's the dot carbon. When we do this reaction, let's say we have that Grignard reagent here. This nucleophilic carbon here is going to attack that electrophilic carbon, pop to the bond to the oxygen to give us this product here. OH, and then that Grignard reagent, CH2 isopropyl here. Well, this is the star, this is the dot. And this alcohol comes from the carbonyl here. Right. Oh, right. Another like type of soft nucleophile that you see are amines, like NH3, ammonia, like or primary, secondary, or even tertiary amines as well. Like everything else, like every other hetero atom cycle, right? So let's look at examples of the soft nucleophiles now. This right here was using hard nucleophiles, which attacks the carbonyl carbon of the enone. Now let's say we have another enone. And then in this example, we're gonna react it with, let's say, this group, 2 copper lithium, 2 H3O plus. You could even say, okay. First step. And then second step, some kind of halo alkane, Br. Okay. Let's now use an enamine here. First step, second step, acid workup. We could even use enolate, which is probably the common one for this chapter, enolate and enamine. Let's say this one, first step, second step, H3O plus. See, we could do NaCN, right? Or this NaCN here could also be hydroxide, OH minus, OR minus, but that's like every other nucleophile. These ones here are the weird ones, the Gilman, enamine, and enolate. Let's label these reactions 1, 2, 3, 4, 5. Okay. Let's look at the first reaction here with the Gilman. And then we have that with this R2 CuLi. Second step, acid workup. Okay. So think of this R2COI as like an organometallic reagent where the atom attached to the copper is the nucleophile, the negatively charged atom, right? This is a weaker version of a Grignard reagent and a weaker version of an organometallic. So which atom here would be our electrophile? Beta. Yeah, the beta carbon. This is going to be our dot carbon. This R group here is going to attack that beta carbon, shift the double bond onto that right there, and pop the double bond onto the oxygen, which will give us this intermediate right here, where this is the dot. Let's make a new bond between the dot and the star. That star is attached to this isopropyl here, right? And then the acid workup step comes in now, where it would protonate the alpha carbon, right? Reform that carbonyl. This alpha carbon here grabs the hydrogen from the acid to give us our final answer, right? Where we see that from the enone, the carbonyl stays if we use a soft nucleophile, but the alkene of the enone disappears and the beta carbon of it has an alkyl group now. Okay. Okay, let's do reaction number 2, which also uses a Gilman reagent in the first step, but instead of an acid workup in the second step, let's say we use a haloalkane. Let's use a different R group. Let's say we have cyclopentane, that 2. Even though there are 2 R groups here, the R group only attaches once in the product. Right? Copper, lithium, first step. Second step, let's say we have that haloalkane here. Okay, same first thing happens. That nucleophilic atom attacks the beta carbon, shift the double bond there, pops the double bond onto the oxygen. Get this intermediate with the enolate ion, connect those 2 pieces. This is the dot, this is the star. Star is attached to this cyclopentane. Right, 1, 2, 3, 4, 5. Okay. What do you guys predict is going to happen next with the second step? Right. Which atom is our nucleophile? Which atom is our electrophile? Right. So whenever you have an enolate ion here, our nucleophile is always the alpha carbon here. The electrophile is going to be this carbon attached to the electronegative bromine. So we're going to reform that carbonyl and have that alpha carbon attack that positive charge carbon and then kick out that leaving group. Right. So this is like SN2, but the nucleophile here is an enolate. Right. So once we connect those 2 pieces, we get our final product here.
So then, like the nucleophile is always the alpha carbon.
Yes, yes. This alpha carbon here. Not the oxygen minus, because when we do its resonance, the negative charge on the carbon is less stable than the oxygen minus. Star that, dot this, attach what's attached to the dot, which is CH2, and then the isopropyl there. So the difference between this first and second reaction is that in the second reaction, this alpha carbon here gets protonated, which gets a hydrogen there. For this second reaction here, the alpha carbon does not get protonated. It gets alkylated. Right? Because a proton is a hydrogen, an alkyl group is any R group. This is the alkyl group here that got attached to that alpha carbon in the second reaction. The hydrogen there, the proton, is just invisible at the alpha carbon there, which is the hydrogen from this acid workup step. Okay. Now let's look at the third example. third reaction with the enamine. Let's say we have this enone, and then we have this enamine. First step, second step, acid workup. Okay. Enamine is gonna react the same way as an enolate, where the alpha carbon of the enamine is the nucleophile. Right? So let's start that nucleophilic alpha carbon. This is a soft nucleophile, which is going to attack the beta carbon of the enone here. We're gonna reform the iminium bond and then use that alpha carbon to attack that beta carbon. Shift the double bond to that double bond there, and then pop the double bond onto the oxygen there. When we connect that, we're gonna get this intermediate here. The start is attached to now single bond, no longer double bond, that double bond, and positive charge there. Okay. And then from this iminium here, let's say we have if we have acidic conditions and water, let's say water is there as well. H2O plus H2O, H3O plus H2O. Right? This would do two things, the acid and water, to this intermediate. The first thing that it would do is protonate that alpha carbon of the enolate. The other thing that it would do is convert this iminium bond into the carbonyl, right? Because our nucleophile here is water. When we use water to attack that iminium bond, pop that double bond to the nitrogen there, we get that tetrahedral intermediate where we do a lot of proton transfer steps, where we deprotonate the group that we want to keep, and then protonate the group that we want to kick out to get back to the carbonyl. So let's just protonate the alpha carbon first by reforming the carbonyl bond. Use this alpha carbon to grab a proton from the H2O plus. Right? That would get our carbonyl back from the enolate. Right? The water here will attack this iminium ion and then give us this tetrahedral intermediate here. Right? And then we do that whole proton transfer step where we deprotonate the group we want to keep, which is the water that we just added, to make that neutral and a bad leaving group. And then we protonate the group that we want to kick out, which is this amine here, to make that into a positive charge, good leaving group. Right? And then to drive that good leaving group off, we're going to reform the carbonyl and then kick out that amine leaving group there. So the side product is going to be something like this, that neutral amine, and then the intermediate, it's going to be this protonated carbonyl there, where the last step is just to neutralize that carbonyl by deprotonating it. And we made a 1, 2, 3, 4, 5, 1, 5 dicarbonyl. So this is very similar to micro addition, right? Where we had an enolate attack an enone to get a 1, 5 dicarbonyl. But in this case, we use an enamine instead of an enolate. They react very similarly, where the alpha carbon is the nucleophile, right? But then in the second step, when we add water and acid, that converts the enamine or iminium ion back into the carbonyl, right? What happens if I put strong base, water, and heat from this reactant here? What reaction would happen?
Oh, the dehydration.
Yeah, aldol dehydration, and specifically intramolecular aldol dehydration, because we could deprotonate this alpha hydrogen here to create that negative charge on that alpha carbon, and then that could be the nucleophile, and this could be the electrophile here, and that would form a 1, 2, 3, 4, 5, 6-membered ring with the whole intramolecular aldol dehydration, right? So once we did micro addition, we could do intramolecular aldol, which altogether the name of that is Robinson annihilation. Right. Okay. The fourth reaction. Okay, this is basically the same thing we just did earlier, but much faster now because we have, he might not give it into like this form here directly. He might give it in this form here, where he gives you a carbonyl, and with that carbonyl, he uses a strong base, which will eventually lead to that enolate there. Because this strong base here, we look for the most acidic hydrogen, which is the alpha hydrogen here, and generate the enolate ion. And a second step, acid workup. Same thing. Nucleophilic alpha carbon, attack the beta carbon, shift the double bond there, pop the double bond into the oxygen, connect those two pieces. Let's see, dot, star, new bond, star is attached to single bond, there. And then acid workup of the enolate, protonate that alpha carbon here. Right. What would happen instead of the second step being H2O plus if we had CH3, CH2Br, haloalkane? What would happen to the alpha carbon? Would it get protonated or alkylated? Right. So let's see. In the second step, if you had this haloalkane instead, then what would happen is that the alpha carbon would attack that carbon, kick out the leaving group to give you still a 1,5 dicarbonyl, but at the alpha carbon here, we now have that alkyl group right there. Right. In the first reaction, we protonated it, which gave that alpha carbon a proton. In the purple one, we alkylated it, which gave that alpha carbon an alkyl group right there. So the enolate ion can serve as a base or a nucleophile. If it serves as a base, then it gets protonated. If it serves as a nucleophile, it could like attack another electrophile. Yep. Okay. The fifth reaction for this enone stuff is any other regular nucleophile you're used to. It could be, let's say, CN minus, OH minus, and H3. So for something style. Wait, let me do a different color. Right. Okay, let's do the cyanide. CN. Hydroxide. Ammonia. Style. Right. Where all of these soft nucleophiles can only attack this strong electrophile here. shifting the double bond onto that double bond, coupling the double bond to the oxygen, and then somewhere in the mechanism, this enolate gets protonated to reform our carbonyl and give that alpha carbon and hydrogen there. And then somewhere in the mechanism as well, these things here will get deprotonated because when the sulfur and nitrogen attacks the beta carbon, it will have a positive charge because it's neutral right now. When it gains another bond, it will have a positive charge. But the cyanide and hydroxide ion will not get deprotonated because once the alcohol attacks the beta carbon, it becomes that neutral thing already. Right? When the cyanide attacks the beta carbon, it becomes this neutral nitrile group already.
You go back up, I just wanted to see the acid workup.
Yeah. Acid workup here. Right. So the one in black is protonation of the alpha carbon by reforming the carbonyl. And then we know that when we shift this double bond to that carbon there, that carbon is going to have a negative charge. And this negative charge alpha carbon can be a base by protonating some kind of, by getting protonated by coming strong acid, which gets this protonated alpha carbon here. Or this negative charge here can be a nucleophile, which can attack some kind of electrophile like α-Alkylate to get alkylated here. Right? In this case, this is the hydrogen. In this case, this is an alkyl group. This electrophile here does not have to be α-Alkylate. It could be another enone.
Yeah.
Right? If it's another enone, then what kind of product would you get from the thing here? Like, what kind of what's the name of that product? When you have an enolate attacking an enone, how many carbonyls would we get from that? Two carbonyls, right? But what's the relationship between those two carbonyls? This is going to be microaddition because whenever you have an enolate nucleophile attacking an enone, that's microaddition. And then there's a specific name for the product of microaddition. 1,5-dicarbonyl, right. So when we use an enone here, a carbonyl is going to be 1,5 from this carbonyl here. So 1, 2, 3, 4, 5. A carbonyl would be this carbonyl here if you use an enone. Okay. And at that point, you can do intermediate Aldol to finish the round.
Well, this one in purple is the same as what we did in number 2, in the second reaction. So
Yeah.
it's just for the different starting rate.
Right. It's the same exact thing that we did here in yeah, number 2, we alkylated it, but different starting reagent.
And then the process is
Yeah.
with acid workup, it's just it's adding convention, but adding the same way all five times.
Right. All 5 reactions always forms an enolate ion here. From a soft nucleophiles, right? Because all of these reactions here are coming from soft nucleophiles. But if we look at the hard nucleophile right here, we do not form an enolate. We form an alkoxide, an RO minus, which gets protonated to alcohol. Next. Okay.
So in general, with hard nucleophiles, we use 1 alcohols.
Yeah. Yeah, in general. We always form alcohols as a product, but in synthesis, if you don't see an alcohol there and you see bromine instead, then the reaction that is PBr3, right? PBr3 would convert that alcohol to a bromine. And then depending on what kind of hard nucleophile you use, the thing attached to the carbon is going to have either a proton from a reducing agent like LiOH4, or it can have an alkyl group from an organometallic like Grignard or organolithium. Okay. Where these two are the strongest organometallic reagents. If you use a weaker organometallic reagent, the copper lithium Gilman one, which is the first and second reaction we did, those alkyl groups will attach to the beta carbon instead, because this is a soft nucleophile, R2 copper lithium. And the R group only attaches once to the enone. Okay. Oh, okay, this is the last reaction. I wanted to see what chapter 18.
After you finish that, can you go over like some of the things that Mascal did in lecture?
Yeah. I'm gonna check his lecture slides because I didn't go to his lectures, and then there are some things that I looked at the slides and then I didn't go over content review session, but I'll go over that after this last reaction here, which is gonna be what was it? Isomerization. So this is related back to midterm 1 with the alkene. Isomerization of, let's say, beta, gamma, unsaturated carbonyls. To make an alpha beta unsaturated carbonyl. Because isomerization would convert a less stable double bond into a more stable double bond. So we're going to relate that concept to this new material here. If we have this beta gamma unsaturated ketone, carbonyl, in acidic or basic conditions, water is a solvent, we are going to shift this double bond to make a double bond here. Right. The reason why this happens is because this double bond here is more stable than that double bond over there, right? Let's say we had another, it's not just because of the substitution, because let's say they are both di-substituted like this, right? That's a methyl group. If they're both di-substituted, the next thing you have to look out for is which one can do more resonance, more conjugation. The double bond that's alpha beta to the carbonyl can do resonance with the carbonyl. The double bond that is beta gamma to the carbonyl cannot do resonance because of this sp3 roadblock here, right? Which is why when you put that alkene under some kind of acid or base, it would isomerize, shift over to make a more stable double bond. No, it's gonna come back. sp3 roadblock. Let's see. Okay, and we'll go over the mechanism of both acidic and basic conditions for this reaction, and then move on to Mascal's lecture stuff.
The double bond is on the alpha beta position, but it's cis. Does it rearrange to become trans, or does it stay cis?
Oh, that's a good question. It would prefer to be trans.
So what?
Yeah, it would rearrange, yeah, to the trans isomer. Yeah, because of steric hindrance, right? That's a good question. That's a good question. Right. An alpha beta unsaturated carbonyl can convert to another alpha beta unsaturated carbonyl, but the difference is the cis and trans isomer. Like a cis version would isomerize into the more stable trans version, right? Which is still the same concept. Less stable alkene isomerize to a more stable alkene. I got it. No. Okay, there we go. Mm. Okay. Right. Yeah, so if we have this alpha beta unsaturated carbonyl that is cis like this, we could isomerize that into a trans alpha beta unsaturated carbonyl using the same reagents, acid or base under water. Right. Let's do the mechanism of both in acidic and basic conditions. Okay. So in acidic conditions, we are going to look for our most basic atom, which is the carbonyl oxygen. Right. That makes this alpha carbon here even more acidic. So the next step here, we use water as a base to deprotonate that alpha hydrogen and form this enol here. Oh, okay. This is another conceptual question here. From this point, this is the carbonyl form. This is the enol form. We always said that the carbonyl form is major over the enol form, but in this case here, this enol form is more stable than that carbonyl form. Do you guys know the reason why this enol form is more stable and major than that carbonyl form in this specific structure?
Because conjugation.
Yeah, because conjugation. If there's conjugation that is able to happen with the alkene and the enol, that is favored over the carbonyl form. Right? If this alkene wasn't here, like this alkene was gone, then the major form would be the carbonyl form because there's no conjugation anymore.
So the reversible arrow is like way larger, pointing towards the
This side,
enol.
right, towards the enol. Which is important for like the benzene stuff. Like when you have an enol on a benzene ring, it prefers to be in the phenol form. Right. And then once we get
Wait, shouldn't there be an H on the right one next to the alcohol?
H on the right one.
Oh, yeah. Far right.
Yeah.
Oh yeah, this should be an H. Yeah, aldehyde, not ketone. There you go. Yeah. So we're gonna reform that carbonyl, shift this double bond to make a double bond there, and then use this let's see, alpha, beta, gamma carbon to get protonated by an acid. Right. What that will give is this alpha, beta, unsaturated carbonyl, where the last step is to deprotonate that carbonyl to give us our enone now. Right. The reason why this conjugated system is more stable than this conjugated system is because when we do resonance, the negative charge prefers to be on an oxygen rather than a carbon, right? Because oxygen is more electronegative than carbon, making the oxygen have a better time holding the negative charge.
So is this mainly like a good reaction in synthesis if you want to, like, if you're trying to make something that you don't react like it, but like the double bond is like too far.
Oh, too far. Yeah. That's right. And then from this point here, you could do like chapter 18 reactions like Michael Robinson. Yeah. This is good for synthesis. Right. Because let's say you have something like this. Let's see. You is example synthesis problem. We could have okay, this is gonna be good. Okay, let's try this synthesis problem really quick. What kind of product do we have, and what reaction do you think made that kind of product?
So 1,5-di.
1,5-dicarbonyl, which comes from micro addition. So we know we want to do micro addition. And for micro addition, What is our nucleophile? What is our electrophile?
Enolate is the nucleophile.
Right.
Nucleophile is the enone.
Nucleophile is the enolate, which can come from an aldehyde or a ketone. And then the electrophile is an enone, alpha beta unsaturated carbonyl. What do you think this starting material can make? Is it more likely to be the enone, or is it more likely to be the enolate? Enone, right? Because we see that it's a very long structure where this alcohol can become a carbonyl. How can we convert this alcohol into a carbonyl here? 118A. PCC, right? And then once we have this carbonyl, we want okay, yeah, we want an alkene here to make the enone. What reagent can we do to make the? Let me make this a little bit more tricky. I wanted to use the isomerization reaction, but I just realized that you didn't have to do that. Yeah, you have to go on this one, right? What I tried to do is make you guys do like the LDA to make the less stable alkene and then isomerize it, but then like you didn't have to do LDA. You could just use the smaller base to automatically go to the enone, right? Now, okay. So what's the next step here?
Elimination.
Yeah, elimination. Any strong base, let's say hydroxide underwater. Elimination, E2. Create that double bond right here. But this is not an enone. It's not an alpha beta unsaturated carbonyl. It is too far away. It is beta gamma unsaturated carbonyl. Now, this is the new reaction that we just learned before the synthesis problem. Right?
H2SO4, H2O.
Yeah, H2SO4, H2O. Oh, it's technically a mutant one reaction isomerization, but the new material concept of how the conjugated alkene is more stable than an unconjugated. Well, that's kind of old material too, but yeah, isomerization. Right. Which now gives us our enone here. Right. And I think I messed up on something. Let's see on the product. Okay, let's put that there. Okay. Okay.
Oh, nice.
Yeah, with the enolate. So what disconnection can we make to find the enolate? Yeah, this connection between 2 and 3, because we know that this 3 here was that beta carbon there, right? Which was the electrophile. This makes this 2 the nucleophile. And that's the new bond that made from the enolate attacking enone between 2 and 3. So we know that the carbonyl is that acetone there. But we can't just put that there. What do we have to include with this acetone to make that into an enolate?
NaOH.
Yeah, NaOH.
In synthesis, would you also just be able to put the enolate, or is it like typically different show like what makes it?
Yeah. In synthesis, Levens, Nasseri, and Helix allows that as the reagent on the arrow, right? Which is the same thing as if you put an acetone there under base. That's the same thing, right? So you should be able to get points by just putting the enolate like that. Which that's the star of that. Yeah. 1, 2, 3, 4 step.
Wait, does Mascal addition care about temperature?
Not micro addition, Aldol. Aldol does. Yeah. At Aldol, if there's high temp, you go all the way to dehydration to create the enone. If there's low temp, you stop at the Aldol product where the alcohol is beta to the carbonyl. Nice.
Could you do the electrons for that last step?
Oh, for this last step here?
Step?
Yeah. For this micro addition one, let's do it. Let's see. Okay, we have. Okay, so here's another tip for the midterm as well. Right, this thing that I just drew right here is going to be the exact same thing as this. It does the same reaction. The reactant here is just the enone, and the reagent is just the carbonyl. The reactant here is the carbonyl. The reagent here is the enone. Like it doesn't matter like what's on what, like what's on the arrow and what's on the reactant. They do the exact same reaction. So if you see like they're switched up on the usual way that you learned it on the exam, like don't get confused about that. Just think about like what you have reacting with each other and like what kind of catalyst or base or acid, right? Because these two things, they look different because they're like oriented differently, but they do the exact same reaction, which is a micro addition because we see that this is going to form the enolate and this is the enone. Enolate plus enone equals micro addition, 1,5-dicarbonyl. Okay. Okay, so I'm gonna do the first way because that is our reactant in the synthesis, the enone that we created, and we brought in the enolate, right? So the mechanism here, we are going to deprotonate the alpha carbon of this carbonyl to generate the enolate ion here, right? Now that's the soft nucleophile, not a hard nucleophile, which will attack the beta carbon of the enone. We form that carbonyl, use this alpha carbon to attack that beta carbon of the enone, shift the double bond there, pop the double bond onto the oxygen, connect the two pieces together. Dot, new bond between dot and star. Carbonyl. Last step here, use water to protonate the alpha carbon of this enolate here to get our 1,5-dicarbonyl from Michael addition. Right. The takeaway here is that the nucleophile is the enolate, the electrophile is the beta carbon of the enone, which would eventually form your 1,5-dicarbonyl. Let me make a quick chart for you to determine the difference between Aldol, Michael, and Robinson. Right. All of these reactions will happen in basic conditions. The reason why is because we want to generate the enolate ion, which is the nucleophile in all of these reactions. Nucleophile for Aldol, Michael, and Robinson. Right. Okay. If your electrophile is a carbonyl, it can't be any other carbonyl. It can't be like carboxylic acid, ester, amide. It has to be either a aldehyde or a ketone. Right. This reaction is going to be Aldol condensation or dehydration. Dehydration if you have heat. For the condensation product, the product is going to be an aldol. An example of an aldol is that carbonyl, and beta to it is an alcohol. For dehydration, the product is going to be an enone. Example of it is that right there. So this is the aldol dehydration product. This is the aldol condensation product. If you see these in synthesis or predictive reactant kind of problem, you know that this is coming from aldol condensation or dehydration. If you see this as a product, don't put heat on the arrow. If you see this as a product, do put heat on the arrow for dehydration. Right. If your electrophile is an enone, the reaction here is Michael addition. Right. The product is going to be a 1,5-dicarbonyl. Example of that. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Right. Robinson is a little trickier to see. The nucleophile for Robinson is still enolate. But it combines these reactions here. Let me make that as a separate thing. Right. Robinson annihilation is the big one. No problem. The first step of Robinson is Michael addition. And then the second step of Robinson is intramolecular Aldol condensation or dehydration, depending if you have heat. Most likely dehydration. Right. And then the product of Robinson is a cyclic enone because of the intramolecular reaction. All intramolecular reactions always forms a ring, a cycle. Cyclic enone coming from dehydration, or cyclic aldol coming from condensation. Right. Another thing for aldol reaction is that there are 3 types: self-aldol, mixed aldol, and intramolecular aldol. Michael, you could also have intramolecular Michael as well. Yeah, Michael, you could basically have all three types: self, mixed, and intramolecular. Wait, self. Yeah, self. That's that. Mixed. Yeah. But the more common one is self or intramolecular. Mixed is a little weirder. Yeah. Okay. Yes. Okay. So let's go back to the isomerization last reaction here, where now we're going to do the mechanism in basic conditions. If we have a strong base like hydroxide, we're going to look for the most acidic hydrogen, which is the alpha hydrogen here from the carbonyl. That's going to generate the enolate ion. And then the next step here, we're going to reform that enolate ion, shift the double bond to make that double bond there, and then use this gamma carbon to get protonated by water. So basic conditions are always faster than acidic conditions, the mechanism, because there's less proton transfer steps. So that's it for basic conditions there. Right.
Do you think after we go through the Mascal reactions, we could do like some synthesis that like combines like
Oh,
17 and 18.
17, 18 reactions. Yeah, yeah.
Yeah.
We could go over that too. Uh-huh. Let's go over like before the Mascal stuff, like the ones that Kevin mentioned. Your name's Kevin, right? I think. Yeah. Kevin mentioned, which is the cis to trans alpha beta thing. So let's say we have this H2SO4, water, and then we make a trans one, right? The first thing, we look for the most basic atom, which is the carbonyl oxygen. Protonate that, kick that out. Have that. Right. And then once we have this here. Okay. So this mechanism here is not going to be the same as the mechanism as we did earlier, because we already have the alpha beta unsaturated ketone, where usually the next step here is to use the conjugate base to deprotonate the alpha hydrogen and form the eno here. But we can't do that anymore because that's going to break the octet row here. We can't form an eno there. So the first step here is going to be the regular midterm 1 alkene cis to trans isomerization thing. We're going to form a carbocation on the alkene here. Midterm 1 reveal, which carbocation is more stable? This carbon or this carbon?
The one that you're on. Yeah.
Yeah, this one right here. Even though they're both equally substituted, this one is conjugated. It can do resonance. This one here is way too far away to do resonance with that. So that's why this one here is going to be the more stable carbocation, even though they're both equally substituted. Resonance will be the next factor we look at. So that's why we use this carbon here to grab the hydrogen, because we want this carbon to lose a bond to get that positive charge on that position. Once we have this positive charge, we can now rotate this single bond to the trans-like configuration, and then do elimination to get to the trans alkene. Deprotonate, double bond, get that. Yes. Yeah, I think in this example here, from cis to trans, it can only happen in acidic conditions. In basic conditions, there's nothing to deprotonate here, or there is this alpha hydrogen to deprotonate, but that wouldn't help us convert the cis to trans, right? We want to make this double bond here to a single bond, so then we could rotate it. To make that double bond to a single bond, we have to use acid to make that carbocation, and then you can rotate it. Nice. Okay, Mascal's lecture time. Let's see. For the next week, I'm gonna go over like the mass spec stuff because I'm not too familiar with the mass spec, like the Nucleophiles rearrangement or something like that. But we could go over like the reactions. I'm not too familiar with the the mass spec stuff yet.
It's gonna be like mass spec, like maybe 2 like multiple choice questions.
Yeah. Yeah, I know. Okay, let's pull it up. 28 and 30, Tuesday and Thursday.
I think that you go over the hydrogen deuterium exchange and then α-Alkylation.
Alpha-Alkylation. Oh, I think I covered that today when we alkylate the alpha carbon from a eno or an enamine, but we could go over that again. Let's see. I think it's this one. And let's do today's as well.
I think in today's lecture notes also there's like a list he typed up all the reactions that.
Oh, at the end of today's lecture.
Some.
Let's see.
It was like, oh, it was like,
When he talked about chapter 18 or before he talked about chapter 18? Before. Vidig.
Oh, and then he said we don't need to know
Wolf Kushner.
the not the Bayer-Hilliger test, but the other two, like the ones with the copper and
Oh, the copper and silver Frading's test, tolerance test.
said those like
Yeah, they're more for lab to test for methyl ketones or something like that. Yeah. Right. Okay, let's go back here. Nucleophiles. Yeah. This we went over, which hydrate is another name for geminodiol, where we have two alcohols on the geminal position at the same carbon. This right here motion transfer. Yeah. Acetal formation. Hemiacetal. This right here, acetal. Equation. Okay, know this. Wait, let's see what this is talking about.
it's just the rate law.
Oh, the rate law. Let's see this.
You trying to say that if you take away water, the reaction goes faster?
Right. Le Chatelier's principle. Take away water, it would want to go more this way to balance out the thing. Okay, cyclic acetal, protecting group. Yep. Bayer-Villiger. Migratory aptitude. Hydrogen is higher than tertiary. Cyclohexane is in between tertiary and secondary. Secondary is the same as a phenyl group. And then primary methyl. Yeah. Thioacetal protecting group. Yep. Yeah, reducing the thioacetal all the way down to alkane using a H2 catalyst. Oh, okay. So this right here is different. We did not go over hemiaminal. It's very similar to hemiacetal, right? Where a hemiacetal is when we have a carbon bonded to an OR group and the other half OH group. That's half OR, half OH. Hemiaminal is half OH, half amine.
It's just halfway through the amine mechanism.
Yeah, halfway through the amine mechanism, right? Which this I would know for vocab purposes. Vocab purposes, yeah. Hemiaminal. Okay. Yep.
So like, I was just curious, like in general, would you say that these reactions, like the acetyl aminal, like all those have like synthetic uses to them?
Synthetic uses, let's see. They can be used to, let's say, like from this point here, this is nucleophilic, where we could use some kind of nucleophile to attack, and then that nucleophile could be here, and then we have an amine there. So in the product for synthesis, if you see an amine and coming off of the same carbon holding that amine, you have some kind of a nucleophile, then you know that it could come from an imine there.
But do you like mainly see these in predictive products or?
Yeah, many stages in predictive products. Like
Yeah.
when you sent me the text of your the synthesis column for your sister, like
Oh, yeah,
that had a carbonyl there with this kind of synthesis column, right? So this does have synthesis as well, not just predictive product, right?
Are hemiaminals stable?
Hemiaminals, not as stable. Hemiacetals, hemiaminals, not stable because the alcohol here is very like reactive, and this carbon here bonded to two electronegative atoms is very partial positive, unstable, unhappy. But acetals are relatively stable. They could exist, like OR and OR. And the way that you could think about this is that these are ethers, R, OR. And in 118A, we learned that ethers are relatively unreactive because they're stable, right? But in this hemiacetal here, We have an alcohol that is very reactive, making this unstable. Right? This one creates an imine, enamine, enamine, enol, Wolff-Kushner, which completely cleaves off a carbonyl into the alkane here. So like this carbonyl here gets cleaved off to get this final product for Wolff-Kushner.
Okay, I think he wants us to know.
Oh,
You
dang.
said it's a 118.
Yeah.
Oh, 128.
Or one, yeah,
128. Right, right. Let's see. Hydrogen nucleophiles, NABH4. Oh, yeah. 118A reduce the aldehyde to alcohol. 118A, 118A. Carbon nucleophiles. Yeah. This nucleophile here will attack this electrophilic carbonyl carbon, form a cyanohydrin here. And then this O minus would get protonated by like the H from the HCN. Organometallics. Oh yeah, 118A, 118A. 118A, yeah. All these organometallic ingredient stuff are 118A. RMGR, RLI, or RMGR, organolithium gradient reagent. Wittig reaction, we went over that. Yeah, yeah. Yeah, we went over the trans version as well. If the ylid and or carbonyl is conjugated, then your major product is the E isomer. Right? If it's not conjugated, then your major product is the Z isomer. Yeah. Okay, now, oh yeah, carbonyl, enone, electrophilic, yeah, enolization. We went over this. This one here is alpha protonation because we're using this alpha carbon as a base, which when we use strong acid, it gets protonated. If we use like RX, alkane, it will not get protonated, but it will get alkylated, where we're gonna alkylate the alpha carbon. Right? Let's see, I think he's gonna go over that after this one here. These one are just the different bases that he could show that could deprotonate that alpha hydrogen to form the enolate. Enol is the protonated version. Enolate is the deprotonated version of an enol. Right. Oh yeah, this one here. This is most likely going to be kinetic. Vocab question: kinetic versus thermodynamic. Relate this back to the last midterm. Thermodynamic makes the more stable double bond. Kinetic will create the more stable intermediate.
Is that just related to the like how exothermic the delta H hydrogenations of the double one for the thermodynamic?
Yeah, right. For the thermodynamic, this one here is more stable. Here, less exothermic, right? And in the previous examples, when we worked with conjugated dienes and HX and X2, the more stable intermediate was the carbocation that we're looking at, right? And then the thermodynamic is the more stable double bond. In this example here, no carbocation is getting formed. So the intermediate here, you're going to think about steric hindrance. That's the difference between what we talked about earlier with the conjugated dienes and carbocations and this reaction here. The best way to think about it is that the kinetic product is the first thing that gets formed, the easiest thing that gets formed. Like the first thing that gets formed is not always the most stable thing, right? This is the first thing that gets formed because there's less steric hindrance on the left side than the right side. That's why this is the kinetic product here. But this is not the thermodynamic product because it is not the most stable double bond, right? Yeah. Any questions on that concept? Okay. Another way you can think about it is that thermodynamic requires more time, energy, and heat to get to the most stable product. Kinetic is in cold temperatures and gets formed first from the more stable intermediate, like either less steric hindrance on that side or the most stable carbocation from HX or X2 from conjugated dienes. Okay. Nice. Isomerization. Oh, this is a new thing, huh?
I was just saying if you have like a chiral center, don't
Don't add
try to
acid.
don't try to add acid because then you're gonna lose your chirality, which like chemically like no one wants to do.
Right. Because we want to conserve chiral centers in synthetic uses of our lab. Because this is sp3 hybridized. Once we like do tautomerization back into the eno form, this sp3 atom turns into a flat sp2 atom. When we tautomerize back into the carbonyl, this sp2 flat atom here could grab a proton either from the top side or bottom side, giving you two different enantiomers in this case, because there are no other pre-existing chiral centers, right? HD exchange. Oh, this is tautomerization, but using deuterium. So when you draw that tautomerization mechanism out, you can't leave the H's as invisible as how we've been leaving it as invisible. You actually have to draw out the deuterium ions out.
Use like D2SO4.
Yeah, you can also use D2SO4 or D3O+.
But what's the reason that this one just goes forward until the, is it like, see how like the
Mhm.
alpha carbons on both sides will like fully replaced with deuterium?
Yes, D and then D+. Oh, right. Because once we tautomerize it, you notice how whenever we get this like eno-like thing, the alpha carbon here is the base or the nucleophile, and we could either protonate it or alkylate it. When we protonate it, we don't have an H there. We have a deuterium there, which is why at that alpha carbon, we have deuterium instead of H's, where it goes all the way down, where we could substitute all of the alpha hydrogens into deuteriums like that.
Is that like normally how the reaction like occurs? Like it wants to go all the way?
These are all reversible, so it doesn't have to go all the way to here, but there are rare cases where we have this existing solution,
Okay.
but it can go backwards too. Like when like the H gets like, kicked out, it can go backwards to here.
So you just use H.
Yeah.
And then
H plus H2O.
H2O, yeah.
And then some of the products in the solution would actually be this as well. Like not all of it, but some of it can no problem. See ya. Get substituted instead, where all these other ones are H's. So these mixed things here can still exist in the solution. He's just showing this where this is a possible type of thing that is solution,
Okay.
where we substitute all of the alpha hydrogens. Conceptual, a lot of conceptual things. Yeah. Alpha halogenation, acid catalyst. Okay, so this right here, we've been saying that this alpha carbon here can serve as a base or nucleophile. If it's a base, then it gets protonated. If it's a nucleophile, then it can attack an electrophile. We worked with haloalkane electrophiles, but the electrophile doesn't have to be haloalkane. The electrophile could be X2 in this case, which this alpha carbon star would attack the Br, kick out the Br to get this final product here, right? It's very similar to how we did earlier, like instead of an H or an alkyl group, this is alpha bromination using Br2.
No, but he didn't write that it gets over how. You get the poly.
That's for basic.
Oh, right. For basic conditions, we go all the way down to the poly.
Yeah.
Poly. For acidic conditions, we stop here because once we get this enolate here, right, we will have one bromine here. When we try to draw resonance here and give that carbon a negative charge,
It's stabilized by induction.
yeah, that negative is stabilized by induction, making it a weaker nucleophile. It can't attack another Br there. But in basic conditions, this has a negative charge, which makes it a strong nucleophile, which goes all the way down to the poly alpha halogenation.
And in basic, he also, I was curious because I remember yesterday we like did the carboxylate, but he stopped at the like this the tricep or like the 3 halogens because he was like, oh, that's like 118C when you get into the carboxylate.
Carboxylic acids? Wait, where is that?
Or, like, you know, when you're doing I don't think he wait, did he draw an election? I don't think in basic conditions he went all the way, but like you know yesterday how like we did basic conditions and we had like 3 bromines.
Oh yeah,
That's
in
the
brothers,
transition state. He stopped at the transition state because he was like doing like the next step like gets us like 118C.
Oh, like the leaving
Yeah.
first like that? 118C. Okay. That's weird. That should be 118B, but not 118C. Yeah, that whole thing that it should be 118C, 118B. But it's okay. You guys don't have to worry about like that leaving group leaving. You just stop at the poly halogenated alpha carbon, right? Oh, I think he's talking about like how the final product is like the carboxylate or carboxylic acid.
Yeah, that's what I meant.
Yeah. That final product there, that's the very first section of 118C, the very first chapter you learned, carboxylic acids.
And I was like, oh, like I was talking through like one of the teams, and
Yeah.
he was like showing the point. He's like, yeah, like I mean that happens, but
But the mechanism to get there is 118B. The final product is 118C. Yeah. Let's see, ketones only. Okay, this is the alpha alkylation that we talked about earlier, where this will get alkylated by attacking a haloalkane to get that alkyl group instead of an H or halogen, right? This right here is just talking about how these act the same way, like how I talked about earlier. Enolates and enamines are very similar. The alpha carbon is the nucleophile, which these carbons here are the nucleophiles, right? Negative charge, negative charge, negative charge. Okay, so yeah, this is also another conceptual thing. This is the most reactive because we see that there is a full negative charge on that oxygen there. This is the second most reactive because this is neutral. This is also neutral, but do you guys know what factor makes this more reactive than this more nucleophilic than this?
Less electronegative.
Yeah, this nitrogen here is less electronegative, more willing to give up its electrons and attack. Oxygen is more electronegative, it wants to keep its electrons. It's not willing to give it up as much as nitrogen. So that's why this is less reactive. So that's another conceptual thing. This one forms an enamine. We apply that enamine. This one forms the, yep, no problem. Enamine, because this is a secondary amine reacting with the carbonyl enamine. This enamine here, it's like an enolate. We have RBR or RX, which will alkylate the alpha carbon, which is that right there. And then this H3O plus here, I said earlier that it will convert the iminium bond back into the carbonyl, right? For this one here, we tautomerize it to the enol. Okay, this is when he talks about aldol here. He ended on aldol reaction, right? Where the nucleophile for aldol we said was the enolate or enol, and then the electrophile is the carbonyl.
Wait, he went over this in like 2 seconds.
In 2 seconds. Oh,
this is self-aldol, right?
Yeah, this is self-aldol because it will attack itself. Self-aldol. After this, it's gonna go over mixed aldol and then intermolecular aldol and then Michael and then Robinson. Okay, but he went over all the stuff we went over today with the alpha-alkylation, alpha-protonation. He didn't go over soft and hard nucleophiles yet with the Grignard organometallic reducing agents, but he'll probably go over that sometime next week or yeah, next week. Right. Synthesis problems now for 17 and 18.
Yeah. One question for the mixed aldols. Does it like, let's say like hypothetically you were given like, you see how like over there, like he shows the two aldehydes, they're the same. You could show like you can make one that emulate and then you one is a carbonyl.
Great. Yeah.
If you for the like, does it matter like which is which? Like, let's say you had like one that's like more substituted or less substituted. Like if you're doing like a mixed aldol, like and you had to like pick, or is that not how it works?
Yeah, if it's mixed, then the difference is not that big. You'll get like mixed, like you get one version and then another version, like another version, and then you get like multiple different products.
Yeah.
Right.
Yeah, we did that. Okay.
Yeah, no, he's gonna go over that next week too. Okay, we finished all of the chapters. Now just practice. Today and next week, final review. Okay. Chapter 17 and 18 reactions. Let's go. Let's see. Next.
If a Robinson
Yeah.
conversion does it happen in one step, or is it multiple? Like in the synthesis.
Oh, in the synthesis, one step, one reaction, like one arrow, right? But then two different reactions are within that one arrow. Michael first, and then intermolecular aldol. Right. Okay, I'm gonna use some previous reactions too, like from midterm one here. Okay, let's try the synthesis problem here. Grignard, I forgot you could do Grignard too. Mg star. Uh, mhm. Yeah, right. Notice where this CN is relative to the aldehyde. This is alpha, this is beta, right? This CN is beta to this aldehyde here. Let's say like there was a double bond right here between the alpha and beta. What is this functional group here? Enone, right? So let's go backwards. Let's say that came from an enone. What reaction did we do to add a nitrile to that beta carbon?
What's the reaction of the alcohol in this?
Oh, that's the cyanohydrin when you react a NaCN or HCN with a carbonyl. But when we have this enone here, we have two different kind of electrophiles. We have the weak carbonyl carbon electrophile and a strong beta carbon electrophile, where the hard nucleophile can attack that carbonyl carbon and the soft nucleophile can attack this carbonyl carbon here.
Oh, so then you use like KCN.
Yeah, KCN and the acid workup stuff, because when the CN minus attacks that, we form an enolate ion, and then the enolate ion would just get protonated by H plus workup. Or HCN would work as well. But if we use KCN, we gotta follow that up with H plus workup. Nice. Okay. Let's look at the differences between the reactant and the molecule. We know in the reactant we have this 1, 2, 3, 4 carbon chain. Let's say that 1, 2, 3, 4 carbon chain is this 1, 2, 3, 4 carbon chain right here. Let's try to make this aldehyde here, right? How can we make like an alcohol go to the fourth position here? So the first few reactions are one-in-scene or midterm one alkene reactions. Yeah, elimination. But what kind of elimination do we want to do? Do we want to do Zaitsev or Hoffman? Hoffman, right, Hoffman. We want to make the less stable double bond. So what kind of base do we want to use? Turbotoxide or LDA? Nice, nice. Turbotoxide or LDA. a bulky base, which will give us our Hoffman products here. Okay. Let's say this aldehyde came from an alcohol on that carbon there. How can we add an alcohol on the less sub position, the anti-mark position?
Hydration.
Yeah, hydroversion oxidation. First step, BH3, THF. Second step, NaOH, water. Oh, the most important thing, hydrogen peroxide, H2O2. Yeah, that's the thing that makes it anti-mark, and boron as well. Now we have that primary alcohol, which we could convert into an aldehyde by
PCC.
yeah, PCC, not Jones. If we use Jones, that would over oxidize it into the carboxylic acid. Okay. Now, let's figure out how to get from this aldehyde to this enone.
It's on the wrong part of the, I don't know how you have. But you need the,
Right. So, what do you think this atom could be? This alpha carbon here. Could it be the nucleophile or electrophile, that alpha carbon? It's gonna be the nucleophile because for these reactions, Aldol, Michael, and Robinson, the alpha carbon of the carbonyl is always the nucleophile. Because let's say we deprotonated it with some kind of strong base, like OH minus, we generate what kind of ion? Enolate ion, where we see that this carbon here is the nucleophilic atom. Because right, so let's make this nucleophilic carbon here, and then that's the electrophilic carbon there. When we get an enone, what reaction did we do? Aldol, Michael, or Robinson? What reaction makes an enone?
Aldol.
Aldol, right? Because Michael makes a 1,5-dicarbonyl. Aldol makes an alpha beta unsaturated carbonyl or enone. Do you guys remember this connection we have to make to figure out what's the nucleophile and what's the electrophile? Yeah, the disconnection between the alpha and beta carbons here, 2 or 3, right? Where which side did we say was the nucleophile? The side with the carbonyl or the side without the carbonyl? Yeah, right. That makes the electrophile that carbonyl right there. So if our electrophile was this carbonyl, which is the same exact aldehyde as we had here, what kind of aldol is this? Self-aldol. Right, to get rid of the alcohol. Right. So the reagents here, all you need is NaOH, water, and heat for self-aldol. We don't have to include any other carbonyl because this is not mixed aldol. This is self-aldol, which is just gonna form the enolate ion here, and then that enolate is gonna attack itself, which this version is itself right here. Self-aldol as the last step. Well, I don't think Mascal synthesis is gonna be like like this. It's gonna be more like obvious, like because I included Mutin 1 reactions as well.
well, his synthesis is like 4 steps.
4 steps, 3 steps, yeah. The first midterm was 2-step synthesis, right?
Yeah, that wasn't what he had in the key though, because I did the 2 steps and I got a 0 on it.
Oh, did you request
Yeah,
points
yeah,
back? Okay, okay, that's good. Yeah, that's good.
Just like how the series or Leavens or Helix would typically get like a synthesis problem. Still, like,
More so for Nisiri and Levens. Helix, not like
pretty
this.
easy.
Yeah, Helix is pretty much more easy than Nisiri and Levens. Yeah, but I would say Levens is more fair. Okay, another synthesis. Let's see. Oh. Okay, this is going to be like 2 or 3 steps, much shorter than the last one. Okay, let's try the synthesis here. I can give you guys a hint. This is chapter 17 reaction that's going to be used here.
Yeah, that's what I'm confused about. I'm confused with the chapter 17 is.
Oh, like what reaction?
Yeah,
This
so,
is?
like, I thought you can just make a triple bond and then,
Oh, that's Alkyne chapter 14.
yeah. So
Right,
I'm really confused.
yeah. So what kind of alkene is this? E or Z? E, right. And in chapter 17, there is one reaction that makes double bonds. Wittig.
Yeah.
Wittig
Yeah,
reaction, right? Where
That's the one with the triphenyl phosphate.
triphenyl phosphate, right? And the major product for that is usually the Z isomer. If the ylide or carbonyl is not conjugated.
Oh, so you react this with the PPH3.
Yeah.
and
Wait, so this be PPH4?
It would be PPH3, right? Wittig. So first step, PPH3. What that does is SN2, phosphorus attacks that carbon, kicks out the bromine.
Oh, I was thinking about doing this with the benzene.
Right. Oh, this benzene here, we bring in, like we don't create that. We just bring in as a reagent. Right. Positive charge. What's the next step for this Wittig? How can we create this alpha carbon to the phosphorus negatively charged?
mhm. Yeah.
Yeah.
The NBO.
N-butyl, yeah, which looks like that. N-butyl lithium, 4-carbon lithium chain, N-butyl. Strong base, deprotonate the most acidic hydrogen, which is the alpha hydrogen to the phosphorus. Oh shoot, 5%. Which creates this negative charge on that alpha carbon. But then we don't usually see Wittig in this form. We usually see Wittig in the with the double bond, which is the resonance structure of that form. So I'm just gonna make a side note here to show that this is the ylide that we are gonna look at here. Right, where let's say this carbon here of the ylide is that carbon there of the ylide. And this carbon here on the other side of the double bond is the carbon of the carbonyl that it reacts with. Right, which is gonna be this carbonyl right here with its conjugated system nearby. Yeah. And then invisible hydrogen, aldehyde. Because it's conjugated, we get the E alkene because this is conjugated. I know, I know. I know. Okay. 17, 18, 17, 18.
Whenever we use a protecting group.
Oh yeah. That's good. That's good. Protecting your cyclic acetal. Let's do that. Include midterm 1 and midterm 2 reactions as well, or just mostly 17, 18 reactions? Okay.
Oh, yes, the final distribution.
No, yes, no.
Oh, should I include?
Oh,
Yeah. I'll probably include like midterm 1, 2, and the final stuff for next week. But for now, let's do 17 and 18.
I think the 17 and 18 synthesis is literally just going to be 17 and 18. It's like the way that he broke the line up, half of it is like midterm 3, which is just chapter 17 and 18, and then the other half is going to be everything else.
Oh, that happens
Yeah,
everything
100
else.
points is midterm 3, 100 points is the final.
Oh,
The
so
final's cumulative.
yeah, 50% new material, 25% midterm 1, probably 25% midterm 2, probably.
Yeah.
Okay. There you go. Yes. This is a mix of 17 and 18. Yeah. The first half is gonna be 17, the second half is gonna be 18. And one little 118A thing.
You put a ketone on an organometallic.
No, that's gonna do an intramolecular reaction because the atom attached to the Mg will attack the carbonyl carbon of the ketone, right? For that last part there, where you see the connection with the ketone, right? This is the new bond between them. If you see a new bond between things, figure out what is your nucleophile and what is your electrophile, right? Like what could have been the electrophile? Like if you say this is the this is the nucleophile here, what kind of carbon is this here relative to the carbonyl?
That's nuclear.
Yeah, that's nucleophilic, which is the alpha carbon, right? Which can attack what kind of electrophile here that would give this OH?
It's
hold on. Which would be a strong or a hard?
Oh, yeah. Okay, I just realized something. Wait, actually, yeah, never mind.
condensation.
The if we want to make this the electrophile here with the oxygen attached to it, the electrophile is going to be a carbonyl. Right?
Yeah.
Right. And it pops up there, and then it gets acid worked up. Right. So that's the last part. Let's do that last part. Yeah. So this reaction here, what is that reaction called? Aldol condensation, mixed aldol condensation. So we cannot add heat here.
And then wouldn't the aldehyde be protected?
Yeah, the aldehyde would have to be protected first. So let's go backwards. Let's say oxygen, and then because if the aldehyde wasn't protected, then the enolate ion would attack the aldehyde instead, because aldehyde is more reactive than the ketone. Right. So first, let's just do the first thing. PCC it to get the aldehyde and the ketone. Right. What protecting group do we have to use to protect the aldehyde? Like there is one protecting group that selects the aldehyde over the ketone. It's not the one with the oxygen. It's the one with the sulfur, thioacetal, right?
Oh wait, is the oxygen one select for
The less reactive?
The oxygen one selects for the more reactive as well, but the oxygen one, like think of it as an excess. Like it could protect both of these carbonyls. It could make two acetals like that.
What if I wrote one of them?
Oh, one equivalence. Then that would go for the more reactive one, which is the aldehyde. Yeah, that would probably work too. Yeah. We want to protect that aldehyde because we don't want that aldehyde to do aldol condensation. Okay. And then at this point, we do mixed aldol with, we could say that, or you could say acetone with NaOH. Oh, and then also acid workup, H3O plus, to get the neutral OH there. And then this aldol here. This is an aldol because wait. Oh wait, I'm missing the CH2. Yeah, there we go. Hold on. Because beta to the carbonyl is an alcohol hydroxy group. We don't put heat because heat would create a double bond here and get rid of that alcohol there. That would be dehydration. Right. And then the last thing here is just to deprotect it, which is the chemical soup here. Do you guys remember the
3CO2?
calcium carbonate? Right. Nice. And then I don't know if you include this CH3CN and water as well. That little chemical soup that deprotects the thioacetal back to the carbonyl.
And then if you use the oxygen as water equivalent, was it just water and H2SO4?
Yeah, water and H2SO4. If you use the one equivalence diol, right? It would be water and H2SO4. So oxidation, protect the aldehyde, mixed aldol condensation, not dehydration, and then deprotect the aldehyde back to the carbonyl. I'll probably prepare more synthesis problems for you guys for next week here. Yeah. Including midterm 1, 2, and new material. Yeah. Okay. That's it. Any questions? Yeah, that's it. Yeah.
What can you do with your over the summer? Like, then